When you were in freshman physical science, wherever it was that you took a physical science, when you learned Newton's 3 laws, you memorized things like Newton's first law, matter in motion stays in motion. Matter at rest stays at rest unless acted on by an external force. I always, on Newton's second law, I always tease the kids when I write, Newton's second law is basically F ma, and they all laugh, and like you guys don't, but they all laugh, and then they, wait, what did you say? But it helps them remember. If they laugh at something, then they'll remember what they laughed at, right? Newton's third law, you'll remember, is every action has an equal and opposite reaction. That's what you were taught when you were in physical science. This book makes us, it doesn't say that. I looked for the definition. It doesn't say that at all. This book talks about interaction pairs. Well, it makes sense. If every force has an equal and opposite reaction, that means that there's an action force and a reaction force and that they come in pairs. So the book emphasizes that. A force is the result of an interaction between an agent and the system. So if we're talking about a ball and the earth, that's a small earth, that's a very large ball, there is the force of gravity pulling down, but then there almost must be, the ball must also be attracting the earth with an equal force. That kind of blows my mind. Right? So why doesn't the earth move? Hold on to that thought for a minute. For physical science students, I marched you out into the foyer, and someone had rollerblades or a skateboard, and I gave them that medicine ball, that weighted ball, and I said, here, you hold it and stand perfectly still on your skates, and then I want you to throw it to me as hard as you could. And then when they threw it to me, the ball went that way. What happened? Well, the ball went flying, right? What in that direction? What happened to the skater? He went backwards, right? Yeah, you got a good memory what happened. Or else you saw me, you were in college seminar and you saw us acting that out in the front foyer. Now the ball went flying that way, it accelerated that way a lot, but did the skater accelerate a lot? No, there was a significant difference between the acceleration of the ball going that way and the skater going this way. Why was there a difference? I thought for every action there was an equal and opposite reaction, Mr. A. That's what Newton's third law says. Why?
Because the mass of the skater is much more than the mass.
Exactly, right? So the forces are the same. The force of the ball on the skater was equal to the force of the skater on the ball, but they were expressed, that force was expressed through different objects. Yes, force of the skater on the ball is going to equal the, let's see, this is the skater, so it's going to be the mass of the skater times the acceleration of the skater. And this is the force of the ball on the skater, so it's going to be the mass of the ball and the acceleration of the skater. Look at the funny way that I've written F equals ma, right? Skater has a large mass. Ball, not so much. Skater has a small acceleration. Ball has a large acceleration. So this is how you mathematically work all this out, right? It's the same force but expressed through two different objects, right? If you want the skater to move more, then skater's got to lose some mass, right? Okay. Same thing applies when the ball's hurtling towards Earth and the Earth is hurtling towards the ball, and we'll show that in just a minute. Okay. I'm going to try to blow your mind here for a minute. In just a minute. So, I need an object. Here's a ball. Because it's a ball, there's not going to be a lot of friction when it rolls, and it doesn't have a lot of weight, right? So, I'm going to do a little motion with my foot. I'm going to apply a force to this ball, and I want to make the ball go that way. Okay? So I'm putting my foot on the ball, Can you guys? Well, you're not going to be able to see my foot. All right. You can stand up if you need to. It's a really cool trick, right? Middleton, I'm going to ask you to stand up and get out of the way because something might happen that you don't expect. Okay. So I need to push this back because I want to be in front of the camera. We're going to catch this on video and it's going to go viral. All right. Okay. Here's the ball, and I'm going to make a motion with my foot to make the ball go that way, okay? Just imagine what in your head that motion's going to look like, all right? It's going to look something like this, right? Right? All right, now, I'm going to make the earth go that way. Did I just blow your mind? Did you see the earth? Did you see the earth go that way? It's called walking, right? When you walk, you are actually trying to make the earth go in the opposite direction. But what ends up happening? You go forward, right? Why?
Not as massive as the earth.
The earth is way more massive, right? So the earth doesn't move, you move. Same force. I applied a force on the earth to go that way. The earth, that reaction pair, forced me to go that way. And when you're looking at the motion, the resulting motion, the motion of me is much greater than the motion of the earth. Okay? Right?